Okay, hello. In this video, I'm going to calculate the expected value of the normal distribution and its variance. So the expected value, in this case, I'm talking about the mean, and then we'll also do the same for the variance. So let's start with the mean. So let's look at the expected value of a variable x. In this case, x is a normally distributed variable, random variable. So the expected value is the variable times its probability distribution function. So that's why it says p of x. And this is, of course, we're integrating it over all possible values of x and the probability of each of those possible values of x. And so the probability density function for a normal distribution is this following equation here. This kind of looks blurry for some reason, and I have no idea why, but that's x minus mu divided by sigma. That's how we standardize a variable. So usually you think about this when we do a standard normal distribution or a z-value. It's the variable minus the mean divided by the standard deviation. We square that and divide by 2 here. That's how we're standardizing it. So we have z, as I said, is x minus mu divided by sigma. So we're doing this substitution here. And the derivative of this is 1 over sigma. And so let's restructure this so that we can actually solve for x. We'll solve for x. X equals z sigma plus mu. And the derivative here is basically this is the same as taking dx and then multiplying both sides of this equation by sigma. So we got dx equals sigma dz. This is going to be important because when we do the substitution, we're going to be able to get rid of this sigma here. We're going to have sigma dz, so that those two sigmas will cancel out, and that's exactly what happens here. When I substitute, instead of x, we'll have z sigma plus mu times e to the minus z squared over 2. That sigma here cancels out with the sigma that was here, so we just get dz. So I'm rearranging this again now. So we get z. We're multiplying by this exponent here. So we get z sigma e to the minus z squared over 2 plus mu e to the minus z squared over 2 dz. So I break this apart here. This second value, well, we already know since we've done this already, and actually in a prior video I've proven that the that this is the probability density function, right? This value, this equation right here minus the x, that's the PDF, and that sums to 1. So basically this is going to be 1 times mu. So the second part of this sum is going to be mu. So it's 1 times mu is mu. So we just have to solve this first part over here. So we'll do a little u substitution, let u equals z squared over 2. So du is equal to z dz. So that's going to get rid of this z, because now this is going to be replaced by du, the z dz, right? It's going to be replaced by du. So we get sigma over square root of 2 pi times this integral. And if we work out this integral, it's basically going to be 0, right? Because, excuse me, because this is the same as 1 over e to the mu, and as mu gets closer and closer to infinity, and this whole ratio is going to approach 0, so we're going to get 0. So we get 0 plus mu is equal to mu, and therefore we found that the expected value of this normal distribution is mu. If we were doing a standard normal distribution, we could, the mean of the standard normal distribution is 0, so this would just be 0. So that would work out just as well. For the variance is the expected value of x squared minus the expected value of x squared, the whole thing squared. So let's go ahead and do this. So we're not going to worry about this part here because we just did the expected value of x, which is mu. So this is going to be mu squared, so we don't need to worry about that. So let's just focus on the expected value of x squared. And we do the same thing. So it's x squared times the PDF. So we have this PDF. We did this z substitution, which I already showed you how to do that. So I'm not going to repeat that again. So we're going to get z sigma plus mu. This time it's squared because it's being substituted for x squared, and then there's the rest of the integral. And if we work this out, expand this, we got z squared plus mu. Well, it's the square, right? Times z squared plus mu, which is z squared. Mu squared plus 2 mu z sigma plus mu squared. You can work that out. Use the FOIL method, first, outer, inner, last, if you want, whatever. So this is now this is in a z rather than in an x scale. Like z, I don't know if you know anything about trains, but the z scales are these really tiny little trains that I like. So this is integrating from negative infinity to infinity. So we multiply this out. Basically, we could multiply each of these terms by this little PDF, and if we do so, this is what we'll get. So these are all three of the integrals, right? So we're adding these different integrals. So what I did was I multiplied by the PDF, right? So you can see that. Well, let's see. This integral here is, well, we can pull all of these three elements out of the integral, like, because they're all constants. 1 over square root of 2 pi mu sigma. That can be pulled out of the integral, and then what we have left is z e to the minus c squared, which we just did earlier, and we know that equals 0. So that's this middle element equals 0. So we just did this when we were calculating the means, or the expected value. So you can go back and do that. Look at that if you want. This right here, well, this is mu squared times 1 over square root of 2 pi e to the minus c squared over 2. Well, we know that this is just the PDF of the normal distribution. So this sums to 1. So really we get mu squared times 1. So what we get left is this whole first integral here plus 0 plus mu squared. Pretty cool. So let's focus just on this first integral. I'm going to leave out this is a constant because we're not integrating over sigma or anything like that. So it's a constant. So what we get left is z squared e to the minus c squared over 2 dz. So I'm going to break this z squared down into z times z e to the minus c squared over 2. And the reason I'm doing that is because then I can use integration by parts, and this will work out really well for us. So integration by parts, so we have this product here. We got this mu part, which is going to be z. Oh, sorry, it's not mu, it's a u. Sorry about that. It's a u. This is not a mu. This is a u. I should have drawn it better. That's a u, and the u is equal to z. U is equal. Shouldn't I say u are equal to z? I'm just kidding. The dv is this z e to the minus c squared over 2 dz. Right. That's our dv part. So if we break this up, and this is like a definite integral here. So we got u times v from minus infinity to infinity minus this integral here of v du. So what I need is u dv. I already have that, right? Here's a u, here's my dv, and then I need I need v and du. So I need to find the antiderivative of this second part right here, and then I need the derivative of u. So we got u is z, so du is just dz, right? The integral, the derivative here of the z will be 1. With respect to z will be 1. The v will be the antiderivative, so it's minus e to the minus c squared over 2. So that'll get us what we really want, right? Because if you take the derivative of this, you'll get z times e to the minus c squared over 2. So it's really, really cool, right? Well, actually, yeah, exactly. I forgot that these 2's will cancel out. You take the derivative, but because this is an exponent, the second part will be e to the minus c squared over 2. Okay, so let's see, we got the v. What else do we have? And then we have the dv. We already have that. So now we can just go ahead and plug everything into the equation, and we'll be almost done, right? So we got z times u. Oh, sorry, u times v, right? going to from minus infinity to infinity. This is going to end up being 0 because, again, this is the same as minus 1 over e to the z squared over 2. If you want to do u substitution, you can, but basically this is going to approach 0. It doesn't matter if it's infinity or negative infinity. Infinity is going to approach 0, so we're going to have 0 times sigma squared over square root of 2, so that's just 0. We pulled out the sigma squared here. Let's see, what else do I have to do? Yeah, so we pulled out this, we could pull out everything here, but this first part is going to be 0, and then we're going to be left with sigma squared over square root of 2 pi times this rest of this integral here. Well, we know that what we're going to have is sigma squared times 1 over square root of 2 pi. The first part is 0 again, right? So this is just going to be 0. And then this will equal 1, right? This is the PDF of a normal, just like a standard normal distribution. So this is going to sum up to 1. So we're going to get sigma times 0, which is 0, sigma squared, excuse me, and then we'll have sigma squared times 1, which is sigma squared. So what's left over from the expected value of z squared is sigma squared. And the last thing we have, plus mu squared, because this was just this one part right here of the integral, because we already had the mu squared here, right? So we were just integrating out this first part of this sum, right? So what we have left then is we have sigma squared plus 0 plus mu squared, which is a sigma squared plus mu squared. So that's the expected value of z squared here. And finally, the last thing we need is this last expectation. Expected value of z squared is mu squared. So that's all we have left. So sigma squared plus mu squared minus mu squared is equal to sigma squared. We're done, and this is our variance, which is sigma squared. So we're all done. Awesome, awesome, awesome. So that's it. So we've shown that the expectation of the variable x, remember we converted it to z, but all we have left here is these constants. The expectation, the expected value is mu, and then the variance is sigma squared. And that's what we wanted to show, right? Okay, that's it. We're done. Thank you very much. The next one I'll do is the same, but using a moment generating function.